Okay, we are going to have the final presentation of today, which will be given by David Timmons, who will discuss some of the more problematic ionograms. Yeah, I removed your thing from the thing. Yeah, it's this one, I think. I assume. So some of you have already, like, by doing some scaling yourself, have already encountered a few of the problems. David will now introduce a whole bunch of more of strange things that can happen. And then after that, we can continue either with scaling the data that you were now already looking at, or you can have a look at some of the more complex cases that we collected for you as well. Okay, so David, please.
Right, so I get the, what do you call it, the less advantageous end of the stick. Right, so I have to remember to turn this on. Right, so I'm going to spend the first kind of maybe even half an hour of the talk talking about kind of some of the stuff that you've already been seeing, some of the instrumental artifacts or issues that you get by interactions with the sounder that you're using and the environment that it's in. So local interference from oblique scatter, attenuation, things of that order. And then after I'm done kind of highlighting all the stuff you should probably just ignore, I'll start talking about some of the more complex features that Mikhail and Ivan kind of alluded to earlier today. Spread F. Ivan and Mikhail both talked about that a little bit. I'll give some more examples. Sporadic E, I know a lot of you actually had a little bit of experience dealing with sporadic E in the set of ionograms that you've been given up to now. I'll just kind of give you an overview of some of the basics of how those work. And I'm going to focus in a little bit on, physically what's happening in the ionosphere to produce the weird structures that we're seeing. And I'll talk about TIDs and some auroral precipitation. And the only reason why I'm talking about auroral precipitation is because we had that storm last week where the mid-latitudes very rapidly became the high latitudes. And so if you're going to deal with any data from that event, you need to understand what's happening in the auroral regions. There's some of the kind of the challenges that you might run into with auroral echoes. In fact, I'm not even going to talk about the worst of them. It's just anyway. And then I'll finish off some tips and tricks, and I probably told you most of them as I went through today anyway. So before I begin scaling, I talked about this a little bit as I went around. Ivan and Mikhail talked about this a little bit as well. Best thing to do is to find some clean ionograms somewhere within the time series you're looking at the station you're looking at, and just look at the separation between the O and X mode, and take a note of that. That separation will be very useful if you're trying to, or if you have to infer information about the O mode trace from the X mode later on. If there are no good ionograms that you can infer that from, you can go online to a geomagnetic field calculator and get out the magnetic field strength from that, and you can just analytically calculate the electron gyro frequency. If you take half of that, that's roughly what that separation is going to end up being. So if you don't have an observation of it, ideally you do the observation of it, you can calculate it and have a rough idea of what that's going to be. Next up, as Ivan mentioned quite a bit, be aware of the predicted values or what the ionosphere should normally look like at the station you're looking at. FOE and FOF1, even during large geomagnetic disturbances, are very stable. Or at least the solar production version or bits of them. Obviously, there are exotic features like sporadic E and other things that can make that more complex. But in general, they're very stable. And so if you see a large excursion from what we would normally expect for that station, it's possible that it's something else. F1 layers can often look, or TIDs can often look like F1 layers. And so this is just one way of trying to highlight whether or not, well, maybe do I have to revisit that? Do I have to think about this ionogram a little bit more? And then the last is just to be aware of your restricted or interference bands for that ionosphere. This is just to, if you have a trace that ends a bit earlier than you would expect based off of where the X mode is, or if it looks like it's ending very flat, that might be due to there being a restricted or an interference band in the ionogram, and you will have to extrapolate that trace out in order to be able to get a proper estimate of FOF2. So being aware of where these are can be helpful to discern when you should care about that. Mikhail mentioned this a little bit. These are just these qualifying letters. We didn't really do much of them in the first practical session, but these are really, they give you they're caveats really about the values that you specified for each individual characteristic in the ionosphere. They've fallen a little bit out of fashion because we've kind of transitioned as a field from identifying individual characteristics to trying and inverting full profiles and things of that order. And so a lot of people either don't record them or when they are there, don't pay attention to them. And you have to be really, really careful with them as well, because some of them are say, well, I put a value in, but it's really just a lower bound on what reality was, or an upper bound on what reality was. If you just use that value without looking at the qualifying letter, you end up with a horribly biased estimate, where you would have been better off just taking kind of an average in the middle. So it's just be aware of the qualifying letters. I generally, personal preference, if you have to use a D or E, don't scale. It is better to not put in a lower bound bias estimate of something where people aren't going to look at the information saying what that is, than to do it and then have them use an incorrect value. But anyway, I'm digressing a bit. The most common one that you will probably, you want to use aggressively anyway, is this U characteristic here. It's just this flag. I'm uncertain to some level of 5% or so in the value that I specified for this characteristic. This can be if you have spread F, if you have to make some extrapolation of a trace a little bit. Let's see if I have any of the there. J is also going to be a pretty critical one for a lot of things. Often we can be quite certain of our estimate of FOF2 inferred from the extraordinary modes. So the utility of J maybe not be needed so much, but it's still an often a good one to put in. Excuse me. In addition to the qualifying letters, there are also the descriptive letters, and I'll talk about these are just kind of to say there's some weird feature of some sort in the ionogram, where I had to make some sort of accommodation based on what's in the ionogram. These can be really useful for, say, if someone wants to study Z mode and wants to know when Z mode was. This is a way to put into an ionogram that say, hey, there's Z mode in that ionogram. So they can be useful as a classification system. They're also useful for telling people why you did or didn't scale something. And anyway, I'll kind of throw up the descriptive and qualifying letters a little bit as I go through things. I do encourage people to use them. If your scaling is often easiest to be able, if you want to be able to use these in Artiste, you have to go to that menu with the table, and you have to manually enter them. Artiste with SEO Explorer. And so often it's very useful to have a second screen where you can leave that table on the other screen and you're scaling on one screen, and then just Alt-Tab around to go between them. Just if you want to be able to do the qualifying and descriptive letters without slowing yourself down too much. Right, so we'll start off with environments. So issues with attenuation, just low power, if it's known, old ionosphere. Contamination from oblique sounders, as some of you saw some of that. earlier today. Issues with multi-hop, and some of the results that can come from that. Some of the things you need to pay attention to. And then again, restricted bands and interference. Right, so here's an interesting ionogram from Thule in the middle of the pore cap. And I'm not going to use a lot of high latitude ionograms here, but this is a pretty cool or simple illustration. This is from a few days ago where we've been experiencing a relatively weak solar energetic proton event. And so there's quite a bit of attenuation. And so normally where we'd be able to see the cusp between the F1 and F2 layers here, and at this time of day we normally see a little bit of an E region trace, we don't see any of that. And so dealing with this ionogram can be a little bit challenging. There's also some splitting of the F2 trace from a patch structure within the field of view that we have to deal with. So when you have a missing cusp, you want to use your descriptive letter J, not J. What, sorry? Thank you. Wait, why? No, missing cusp. Oh, now I'm... You can tell how often I use these descriptive letters, right? I often tend to be quite conservative. If I can't reliably scale something, I don't scale it. And I generally encourage others to do that as well. So in this case, I'm talking specifically about the E layer. Let's start with the E layer. So one, we don't have an E layer trace, right? So we can put in a descriptive layer saying, well, there was attenuation, and so we didn't see an E region trace because there's attenuation. That'd be descriptive letter B. If you thought that you weren't seeing an E region trace just because the sounder's lower frequency was too high, which is often the case at high latitudes. FOE can often be 1.5 megahertz, and that can be lost. That could be missing due to attenuation because it's very low frequency, or just because, well, this ionosphere only goes down to 2 megahertz, right? So you might want to caveat why you're maybe not seeing an E region trace during the daytime when you might expect to see one. Of course, it's not uncommon to not have an E region trace. It happens all the time at night, so we don't typically have like a descriptive layer to say no E region trace. It's regular occurrence. So moving on to the more important bit. Sorry, the descriptive letter here for a missing cusp is L. I should have remembered that. I don't know why. And so again, we have an F1 trace, and then we have this big gap, and then we have an F2 trace from there. And so there are a couple options here. We could take the upper side of this and say that our FOF1 is within 5 or 20% below that using a qualifying letter. Or we could take the bottom of this and say that it's between 5 and 20% above and use a different qualifying letter. Or we can try to actually estimate this thing rather than bothering with these qualifying letters. Instead using either interpolation in time or inference using other information. So in this particular case, FOF2, pretty easy to go for. There's a little bit of mode splitting here, but this left side of the trace is the dominant trace. One thing that we can try is to just back off the power threshold like we were doing earlier today. So instead of leaving it at the default 6 dB, knocking it down to 3 or 4 dB and seeing what comes out of that. And when you do that, you get a little bit more definition in this trace, a little bit more of a flat definition in the F1, and this population of echoes here becomes cleaner. But it doesn't really solve our hole that we have to deal with. And so to do that, we do have to start looking at the ionograms around. Where was FOF1 before and after? And when you look at that, you find F1, and F1 is right here. FYI, this was not scaled by me. This is just an automatic scaling that, so this hasn't been corrected. The whole point of this is just show FOF1 is roughly here. If we go to the next trace, yeah, that would be pretty consistent with where we should expect FOF1 to be. If we want to be able to invert HMF2 from this ionogram, even though there's a large chunk of it missing, we can still have high confidence that roughly this is the structure that we should expect based on what the ionosphere looked around that period and based on the information that we have available to us. So we can do this. We have to caveat this, however, when we do this with qualifying letters. You can't give this to someone and say that this is a high confidence scaling of this ionogram. FOF1, I'd likely use a U qualifying letter to say that I'm pretty confident we're within 5% here. And then HMF2, I would also need to qualify that with a U letter or so on. And this is just to show where the qualifying letters go. Qualifying letters, descriptive letters. Right, this is another silly ionogram from high latitudes. There we have happy fun times all the day, where we have even more attenuation. In this case, we're also having a little bit of lacuna effects in the F2 trace, where not only do we have kind of this gap here, but we also have very, very sparse F2 echoes. We're a little bit more confident about FOF1 in this one because we do have more of a vertical section into our into the F1 trace, but we can still back off the attenuation a little bit and take a look, and that gets us a little bit more of our vertical element of the F1 trace, so we can again have more confidence in that. I can put an FOF1 on this and not caveat that. What I will have to caveat, however, is the F2 trace, where we have considerable spread. Generally, you'd have to qualify this again with at least a U qualifying letter in FOF2 and HMF2. But based off of using the ionoson a lot, I know this is reasonable structure for the F2 trace, and it's a reasonable value for the F2 trace given the attenuation that we're experiencing. So high latitudes are a pain in the ass, just to put that straight out there. This is not an almost ionogram at high latitudes. This is all the time. This is all the time. You have to make a lot of inferences. You have to be very careful about what data you use. And you have to aggregate data across, say, multiple time steps and, well, your own experience as well. This is the same personal comment I made before about qualifying letters, but I'll skip that. So you can also have restricted bands. We talked about this earlier, or we saw a lot of this morning with the examples. Here you can just see two little gaps in the ionogram, and of course you can easily extrapolate across that or interpolate across that and not have any problems. However, these gaps can sometimes end up on your F2, your FOF2. And so in that case, you need to use your extraordinary mode trace to infer the value for the FOF1, to extrapolate that FOF1 trace. You can also use the structure of the X mode to try and figure out what the curvature of the trace should be to be able to do that extrapolation. Again, this is, anytime you see this at the top, this is not a manual scaling. This is not a recommendation of how to scale this. I just wanted to put up the ionogram and point to it, and this is the easiest way to get an image. When you do this, when you infer FOF2 from the X mode trace, you should use the qualifying letter J to say that you have not necessarily directly measured this, but you have inferred it, and you have reasonable confidence in having done so. That, unfortunately, is a really common thing that you're going to have to do. Again, the ionograms that we showed this morning are supposedly easy ionograms, and I think the vast majority of you ran into several cases where you had to do some extrapolation of the trace based off the X mode. So that's something that's just a regular occurrence that you have to be very aware of. And if you aren't careful with that, you can very regularly create a bias in even climatology of the F2 peak. So just be very, or F2 peak or FOF1 for that matter. This is just an example of a situation. I'm going to pick on Wallops Island quite a bit this morning, where we have multi-hop, which is fine. So here's our second hop. This is somewhere around the 10th hop, 12th hop, 13th hop. As you go more and more hops, these traces will start to shift vertically. And if you have enough SNR, if your ionosonde is really good, or if the band or the bandwidth the pulse length that you're allowing isn't isn't sufficiently long, you can end up aliasing back your multi-hops into your earlier ranges. And this can actually happen a couple times, especially with Wobbs, who has great SNR. And so you just have to be aware that these traces here are not part of the normal trace as you go through. This is a benign one where clearly it's very obvious that that's not the case. Other times it could be more subtle, it could be more difficult. Sometimes this trace is not here, and all you will see is these. So it's just to be aware that you have to be a bit careful with some of the self-interference that we can get. This is just an example of multi-hop causing some problems, I guess, or not problems, but some ambiguity in your interpretation of the F2 or F1 layer. So here's our E region with a lot of spread. You can see the second hop of that is this population. You can see it's almost contiguous with the F1 and F2 traces here. So you just have to be very careful, particularly when defining, say, blanketing or the cusp of the F1 trace, that you're not actually just seeing multi-hop from the E region below. This is particularly important when we're talking about if you have sporadic E, where there's this descending mode at the bottom. That can very often resemble the initial part of the F1. And so you just want to be very careful that you're not actually conflating a structure that's a second hop as the primary hop of an F region echo. This is a fun one. This is just another example. So we have, sporadic E, then we have the second hop sporadic E, the third hop sporadic E. We have our normal F2 trace here, and then we have the second half of the F2 trace here. This one is an echo that went up, hit the F2 layer, hit the ground, hit the E region, and then came back down. This one is much the same, but slightly different flavor. The echo went up, hit the F region, came down, hit the top of the sporadic E, went back up, and then came back down. And this is particularly common when we have these non-blanketing sporadic E's, where sometimes your signal will go through, and sometimes it'll get reflected. And so you can get various kind of superpositions of these different features into the multi-hop reflections above. And so just be aware that you have to be cautious of, or be aware of the separations between your traces and the relative separations of other elements of your traces as well. So I can infer all that information that I just told you based off of knowing the distance between here and the distance between here and here. That's all. This is an example during the eclipse where the autoscaler had a really rough time. Millstone effectively was saying that FOF2 was 12 megahertz throughout the eclipse. And it was just because they had done these oblique modes, I guess, coincident with the vertical sounding mode. And these are from Alpena. So Artis, in this case, just kind of got a little bit confused. These kind of overlapped with each other, so decided to try and trace along and ended up down the oblique trace. This doesn't happen often. This only really happened at Millstone because they allowed echoes that are much lower in elevation to be classified as vertical than they should be. This would normally never happen. But it's something that does happen once in a while. You saw a bunch of oblique traces in the ionograms that you're looking at before that are normally classified as these different elevations here, different colors. In this case, they just happened to be looking like they came from vertical, even though they were oblique. So just be aware. The way they handle this is obviously just to put your slider here at the proper end of the F2 trace instead of trying to add on all this weird oblique stuff. Oblique echoes are always these kind of sideways V's. They should be pretty obvious to identify. This is another example of interference from, say, a non-cooperative interferer, in this case, a military sounder. So you can see all these kind of slightly angled lines here as we're going through these chirps. You can also see some reflections here that are coming from considerably off vertical. these are again all just signals that are getting into the ionogram by virtue of a nearby military sounder or communications system. In the high latitudes, very often the Coast Guard will create these like very long diagonal structures all the way through your ionograms, which are a bit annoying. Easy way to identify these is just kind of take your time history and propagate through. They're not synchronized to the ionosphere, so they will slide up or slide down as you go through. So they shouldn't remain at the reasonable points. You should be able to pick those out. They don't necessarily have to look like these like little slanty structures or just sporadic-y looking things. You can get normal F-region echo stuff from these. Just again, know that you can use time history to identify them. This is kind of an example where this can be a bit problematic. So here, you could, to some extent, think that there might be sporadic E here. In fact, this is just, again, that interference from the uncooperative sounder. So just be aware if you're seeing these structures, use your time histories appropriately. And all this to say, there's a lot of things that can be problematic that you have no control over. You just have to be aware of them. And the whole point of what I'm doing now is just to kind of give you this kind of overview of all the things that you should just kind of ignore. This one, don't ignore. This is the operator has kept their upper sounding frequency too low, and so you do not have a completed trace here. This is a perfectly great ionogram, but it's just missing the top half. There's a qualifying letter for that. I can't remember not qualifying, or a descriptive letter for that. But the main thing is, this is another example of this. That was during the eclipse in October 2023. The Idaho Falls ionosphere was operating in this unfortunate mode where you just ended up with 8 megahertz and then a little blip down and then 8 megahertz for everyone who was trying to look at the eclipse. And so if you are scaling ionograms from reasonably recent periods and you notice that your trace is running off of the ionogram, just let the operator know. We're not trying to do this. We're trying to optimize our soundings to make the best use of the sounding that we have. And so sometimes we just forget. Sometimes we don't think, oh yeah, I forgot to increase this. We're at solar max. So let them know. They're not unhappy to find out, to fix things. They don't want bad data either, right? Okay, so I'm going to pause for a second and just kind of ask if there are any questions up to this point. Those are all, again, issues with the instrumentation or interference or problems that, bunch of things that you probably should just ignore. Questions? Okay, it's a bit of an onslaught of information, I realize that. You guys will have the slides, so you can kind of have an archive of some of these little things for later on. Okay, since there are no questions, the first up is of ionospheric conditions that can be problematic or challenging to scale are G condition. I'm probably starting with one of the most annoying ones because G condition is very, very difficult to identify. What it is the F2 trace or the F2 plasma density has decreased either below the F1 level or is kind of migrated above the F1 trace so that we don't have a discernible F2 peak. So you will still have an F1 trace in the ionogram, but there will be no F2 trace. And it's very common to accidentally scale that F1 trace as the F2 trace. In an inverted profile, that doesn't cause a problem. The inverted profile will just look like the inverted profile for the trace that you give it. But if you're someone doing climatology and you're looking to model, say, FOF2, and someone has included a bunch of FOF1 in your data set, it becomes really, really challenging because they adhere to completely different physics. The F1 layer is very, very stable day in, day out, given by the blue here. This is FOF1. And there's a geomagnetic storm that occurred here, a subsequent decrease in electron density here. And you can see FOF1 doesn't really change at all over this period, or very much. Whereas the F2 peak given by the red is very dynamic. There's a lot of variability in the F2 peak day to day, and especially during geomagnetic storms. In this case, this geomagnetic storm caused a positive ionospheric response. So we had an increase in FOF2 during the daytime. And then we had a subsequent negative ionospheric response following the storm because recombination rates had increased due to upwelling of molecular neutrals. You can look at the HMF2 and you can see that the increase in density here is commensurate with lifting of the F2 peak by about 100 kilometers into a region of lower recombination rate, and so the plasma density is increased. So as we progress into the storm, I should mention the G condition is incredibly common during storms at mid-latitudes. It's almost a really great indicator that you're having a geomagnetic storm. So the storm progresses, you get upwelling of molecular neutrals, that decreases the FOF2, and to a point where it decreases to where it's ephemeral, it's above the F1 peak, it cannot be seen by the ionosonde. And so you go from having an FOF2 to only having an FOF2 here, to only having an FOF1. It recedes behind the F1 layer. Unfortunately, SEO Explorer doesn't invert the profile if the F2 peak isn't present, so we don't have HMF1 here. But if we did have HMF1, you'd actually see kind of this clear transition straight into the F1 heights here. But anyway, the point is, we have a situation where the F2 trace is not there, and we have to be able to discern what is real and what is not, or what is F1, what is F2. So I'm just going to go through a series of ionograms here. The first is just normal F2 trace, life is good. F2 trace, life is good. F2 trace, life is good. Okay, well, F region is starting to descend as the daytime, or as the sun is starting to rise. Starting to get production of a little bit of an E region trace here. And we're getting a strong cusp developing on the bottom of the F2 trace. We're starting to see a little bit of structuring from TIDs at the end here, but again, we have a pretty well-defined general E region and F2. Here we're getting some blanketing where we don't have the bottom half of the F2 trace, and we're also missing, we're getting some TID activity to the end here. And then, if you noticed over this entire period, that F2 trace just keeps on dropping. Once we get to this point, we can look back at our predicted values, and we find that the FOF2 at this, or FOF1 at this point should be somewhere around 2.7 to 2.9 megahertz, which is right in the vicinity of where this is. And if you look at this trace, you go all the way up here, around 900 kilometers, and this little inflection here is what's left of your F2 layer. That's the F2 trace there. The rest of it's starting to recede behind the F1 layer. Little residual bit of it left, still dying. The gradient at the top of the F region is effectively flat. So we're getting these really, really, really long cusps. And it's gone. And so what we're left here, this might look like a normal F2 trace, but it's an F1 trace. This is FOF1. And so we can trace this out. Later in the day, this is the jump between here and here is about 10 hours. We have, again, really well-developed E region. This is still the F1 layer. This is just a TID modulating the F1 layer. It's trying to trick you. Clearly, the heights are too low for it to be the F2, which should kind of give you a little bit of confidence in the assessment here. But yeah, this extension here is just a TID. Here again, this is just a TID working its way through the F1 layer. This is your FOE. And now we're starting to see the F2 trace starting to descend back into the realm of the living. And then it starts to become really well defined. A rather sudden, just complete eruption of the layer. That TID in the lower F1 has moved its way along. And again, you can still see this place that we were originally calling FOF1 is consistently FOF1. You move forward in time, this eventually kind of works its way down and extends, and then we end up at this, where you get this beautifully clean normal ionogram. So all of this is just kind of the illustration of this process. So we started somewhere around here, hit the minimum, and then as we were recovering, we got overtaken by the F1, and then the F2 eventually came out to say hello. So these, if you're trying to identify, if you suspect that your FOF1 is, or that what you're scaling is actually the F1 trace, check your predicted values. See if your FOF1 that you're scaling is close to the predicted value. That should be your first go. Second, if you scale a long period and then you look back and you say, oh, well, I've got a bunch of HMF2s at 150 kilometers. Take a look back. That is very likely G condition. You very likely just scaled the F1 layer as the F2 layer. And so just be aware as you're going through and try to identify some of the subtle signs that your F2 trace is starting to flow away. Okay. One thing that you did get a lot of this morning was some spread F. Yvonne kind of gave some of the standard advice for that. There are two different types of spread F, or they can be mixed together as well, but we typically classify them as frequency spread and height spread. You typically see height spread more at equatorial latitudes. At high latitudes, you tend to see a lot of frequency spread. We're only really going to be talking about frequency spread because it's the thing I'm most comfortable talking about. Ideally, you'd have someone who's a high latitude or a low latitude, someone who does a lot of low latitude to do the height spread stuff. Because there's some stuff you'll see at low latitudes in plasma bubbles that just I can't deal with. Right. So effectively, yeah. That means that they're coming from away from vertical. They're oblique. So the ionosome doesn't have a fine. It's not a beam, right? It has a relatively wide, it is a beam. It has a relatively wide beam width, and so you can get. You're illuminating a relatively, say a couple 100 kilometer wide part of the ionosphere, and so you can get echoes from across that region, especially if you have coherent scatter from regularities and things of that order, or tilts in the ionosphere that can reflect them back to you. Sorry.
And is it normal to have the only ordinary echoes without extraordinary echoes?
Is it normal to have ordinary without extraordinary? It can happen at high latitudes. It's very common to not be able to have an extraordinary mode. Sometimes it just couples directly out through the ionosphere, which is, we're not going to get into that. But it can happen. Mid latitudes, you're more likely to see the O mode get attenuated more than the X mode. Yvonne looks like he has a comment.
Attenuation, yes. X cycles are attenuated more because of the sense of rotation.
So spread F is just, we have undulations or irregularities operating on the F region. And some of these are scattering echoes, or you're just getting more complex reflections from the ionosphere as well. And these will cause the trace to be either broadened in frequency or in height. Height broadening often comes from these almost resonant chamber effects, where you kind of propagate into a small bubble or hole, and then bounce back and forth inside the hole until you escape. And that causes you can get various different broadened sets of echoes that are actually separated by effectively multiples of the inner scale of the structure that your signal got stuck into. So you can actually do some weird stuff to measure the scales of plasma bubbles and stuff. But I'm not. What's that?
vertical extent, why they are confined to these small frequency bits. If they're supposed to these TIDs or things like this.
I'm not quite sure what you're referring to.
In the ionograms, you've had some, I believe it was more for TID situations, that there were for some frequency bins just these vertical extent, that this is also to the scales of these irregularities.
I'm not sure. I'd have to look at the individual case to. Sorry, it's hard to talk about images and yeah. But show me later, and I'll chat. Right. So again, spreadf. Your kind of standard procedure for spreadf is the following. The trace that's lowest in altitude is most likely to be overhead. Not a standalone rule that can be easily violated at high or low latitudes. The strongest trace is most likely to be overhead. The inner edge of the trace is often most likely to be overhead. And as Yvonne mentioned, the second hop is usually a really good indicator of what echoes are coming from overhead, or what are the reliable echoes that you should be scaling. Again, if you send a signal up, it gets reflected by the ionosphere send it up at an angle, it gets reflected by the ionosphere, it comes back. The second hop, that signal is going to reflect and go the opposite way. And unless you have exactly the same tilt and structure on the other side, it's just going to keep on bouncing away. And so your second hop is going to filter out a lot of those off vertical structures that might be making spread that's harder to distinguish from reality. So again, these conventions, particularly the top three, are not sure-fired rules. They need to be taken together as a composite of information, not in a vacuum. And what I will mention also is a very often forgotten parameter, as Yvonne mentioned earlier, is your FF or your FQ parameter. In your big table that you can fill out with qualifying letters and descriptive letters, this is a parameter that defines the width of frequency spread in your spreadf, and FQ is the corresponding one for height spread in your spreadf. Again, I'm only going to talk about frequency spread today, so I'm only going to kind of mention FF, but it's just that width of the spreading of the echoes. And it's usually, it's technically determined based off of the X mode rather than the O mode. Okay, so again, we have this symbol at the top. So this isn't something I've manually scaled. This is from Artiste. This is a great demonstration of Artiste doing very, very well. You can see it's followed the main, most intense, and also the lower trace at the start of the ionogram, and then transitioned to the trailing edge of the trace as it's gone up into the cusp. We can see in the second hop, it's a bit harder to see in the second hop, but you can see in the second and third hops, this aligns with that mode. And so this is a good scaling. This is generally what you want to do. You want to scale the bottom or the most dominant set of echoes and then transition to the trailing edge. This is a poor example where it does well at the start. You can start to see some stratification here, some separation of echoes, some height spreading, coming from some structures that are off vertical. But you can see, Artiste correctly identifies the bottom of the trace and does pretty well, but then kind of gets distracted by this interference band or restricted band. It kind of goes off to the left. Instead, it should have probably come up to, well, it's hard to do from this angle. It should have come up to about here. And again, you can see that into your second hop right here. This is just kind of a series of ionograms separated by half an hour to see a progression. And these usually are not in isolation. There's usually a set of ionograms that are experiencing spread F. And sometimes you'll start to see some of the kind of the symptoms of it, or be able to diagnose some of the reasons why you're getting that. So in this case, we're starting to see a lot of echoes coming from off vertical. But Artiste is doing a good job here. It's identified the dominant trace and then again the trailing edge. In the age of modern ion zones where we have angle of arrival information, it saves you a lot of trouble. At high latitudes, the ionograms that I typically use don't have polarization or angle of arrival, and so you can't unfortunately just directly rule these out. You have to start using other higher order, reasoning to be able to get rid of them. But in this case, it's a beautifully well scaled ionogram. Again, dominant leading edge or bottom edge, and then trailing edge. Same bottom, trailing. Again. Yeah.
If you go too back, that was actually better.
Oh, I know. I'm not. I'm ignoring the RT scaling. That was me saying, "Yep." Again, bottom, trailing edge. Look at the point, not the thing. Yeah, of course. This. Well, yeah. I guess I'm not sure I should be talking about RTs too much, but yes. RTs includes confidence scores. It includes information to tell you whether or not you should have some reasonable confidence or some idea of whether or not you should trust that trace. These numbers have meaning. They're not just like a score out of 100. Each number has a different particular meaning, and it's dependent on a feature within the trace itself. So, sorry, I don't know, Ivan, if you had anything else you wanted to. I'm sorry. We're good. I realize that we pick on Artiste a lot, but it does incredibly well, like 95% of the time. It's just when, unfortunately, weird stuff starts happening. Usually the biggest problem that I find is it's usually in the vicinity of these interferers or these restricted bands that it starts to have some more trouble. Yeah?
So in this case, when it's not able to trace it, what is the sea level equal to 33 signified? What does it mean?
Yvonne?
11 is the best, 55 is the worst.
The numbers mean something, but no one knows what.
Yeah.
No, each digit is different or has a different meaning as well.
There are multiple approaches to that. Yeah, we standardize everything to something called not sea level, but sea score, confidence score. That goes from 0 to 100. 50 and up are acceptable in a simulation if you're running in a simulative model for ionospheric weather. Everything below 50 is highly suspicious.
Yeah, and even then that depends on the parameter as well. Like, the score is a deduction from a total score of 100, dependent on whether or not there are different features that are problems. And so you can get a score that can be gone to by multiple different ways. And so some of these problems are more problematic, say, for HMF2 and don't mean it, like are fine for FOF2. And so just be aware. There's great documentation on it.
If you ever use the data, for instance, if you get it from the Giro repository, you should be careful that if the confidence level or confidence score of data is not good, you should not trust this data. But if the score is good, you should still not trust the data. Because you only get one confidence level or confidence score for the entire ionogram. The point that David is just making is very important, that it might be that most features are fine, but one is not, and if that's exactly what you're looking for.
Also, within the SEO files, if I'm not mistaken, it actually lists each individual deduction separately. That information is in there as far as I recall. So you can actually look at those deductions rather than looking at the total score, if that matters for your application. That's an RT's topic though, not a scaling topic. We're trying to deal with the situations where we can't necessarily trust RTs rather than determine when we can. Right. This is a beautiful case where the second hop really, really cleanly shows you where the correct trace is. Again, bottom, back, edge. You can see there's starting to be some problems because of these restricted bands. But again, our second hop here is really clearly guiding us to this region here. With this one, because it's on the edge of a restricted band, you might also want to just double check that the separation between our X mode and our O mode is appropriate. You might have to extrapolate slightly into that little bit of a restricted band. It's only like a fraction of a megahertz, but for some people it matters. Another example, same thing, bottom and back. These are really not all that exciting. This is one with a lot more complex other echoes, but again, the second hop is really clearly defining where we should end up going. These should be relatively straightforward. Spread F is very common, except for in high latitudes or latitudes where you get some more exotic features. You should generally be able to handle these okay. Same, again, ignore the black line, but you know what to do. Bottom, back. Okay, so that's spread F. Next up are sporadic E. And again, you saw a lot of sporadic E in some of the ionograms that you were looking through this morning, some of the more simple ones. I don't think there was anything with a really particularly intense sporadic E in it, maybe a megahertz or two. But we'll get into those. Sporadic E are just these thin metallic ion layers that are produced by convergence by either gravity waves or tides, or if you're at high latitudes, external electric fields. Depending on the orientation of the magnetic field, you can get compression from an externally imposed electric field. And so that, if you have, if you don't have metallic ions present, these tides can still compress and structure the E region, but they won't form thin, very dense layers. They'll just have small undulations. And I'll show you some examples of what that really means. If you have metallic ions have very slow recombination rates. Typically, they require a 3-body recombination reaction to be able to I guess, recombine. And so that means that these ions can be operated on by this convergence for very long. And so you can get very, very thin, strongly compressed layers that become very dense. Now, because they're very thin and dense, and they often have holes, well, I'll talk about that later. I'm not going to bother that. You can think of sporadic E as being like conventional clouds, cirrus clouds in the atmosphere, for that matter. And they operate very similar to that. Horizontally, they can have very long scales. They can be wispy. They can have little holes in them. They can have regions that are, more thick, less thick to an HF signal. And so this is just a classic sporadic E here. So we put our HES and our FOES here. In this particular case, we have, I'll just use my icon if it shows. Yeah. We have blanketing, so the thin metallic ion layer is dense enough and consistent enough over the entire field of view of the ionosome that we're not able to see the F region until we propagate signals at frequencies higher than the plasma frequency of that sporadic E. Also to note, you do not see a cusp in the F2 trace. Sporadic E, again, are very thin. They're not you're not spending a lot of time with your signal frequency very close to the plasma frequency, so you're not getting a lot of slowing from these sporadic E layers. And as a result, you don't see that exaggerated cusp structure at the start of your F region trace. Another thing to mention, I've started putting my FFs here. We have a spread here, or we also have frequency spread in our F2 trace. I'm calling that about 0.5 megahertz worth. Can zoom in a bit, where you can see the end of our sporadic E around here. I've in Artiste, you can right-click and drop down to select FOES and HMES, or sorry, not HME, H'-ES. In general, you want to put your H'-ES at the bottom edge of the sporadic E trace, and your FOES should be at the end of the sporadic E trace. In this particular case, we're also seeing a little bit of fuzz leakage around the sporadic E, and this structure is some interference also causing a bit of an annoyance. This is not part of the sporadic E structure. We can verify that. We can go to the X mode and trace that back and say we're in the right neighborhood, although we can't necessarily trust that with sporadic E. Other than that, is there anything else to discuss on this one? I think we're in the clear. Right, so of course, sporadic E doesn't have to be blanketing. It doesn't have to stop everything from being able to get through it. Again, if it's quite wispy, it's got little holes in it. It can have regions that are just slightly less dense, more dense. And so if you have an ionosong with a relatively broad field of view, you get some echoes that get reflected off of these sporadic E and some that get through. In this particular case, we have, well, I think I have I'll focus on the F region first. Again, we have spread in the F region. Don't trust the arctice in this case. Although this is a good example of a situation that violates our previous rules. In this case, our dominant trace has an FOF2 here. You can see a coherent structure in our echoes all the way to the top, to the end of this trace. So we're not getting spreading forward, we're actually getting spread across. This is usually indicative of there being a TID rather than necessarily irregularities, where you're actually getting two separate traces that are just kind of overlapping a bit. Right, so on our spread F here, I've just classified that as about 0.8 megahertz using my FF parameter. And then I'm just zooming in. We've got our normal E region trace here, although it's a bit lacuna. And then we've got this downward and elongated structure that is our sporadic E. But you'll note that even though we have sporadic E down here, we still have a clean F2 trace above it. So the sporadic E is not covering the entire field of view or is not that dense everywhere in the field of view. And so you're getting signals that are able to clearly pass into the F2 region without issue. You might actually say, so this here is a second hop of just this portion of the sporadic E. So you could say that this is blanketing up to this point, likely. So there's at least this dense sporadic E everywhere within the field of view, but there's up to this dense sporadic E within the field of view somewhere. Right, and this just showed another example of a situation where you can have both blanketing and non-blanketing. Blanketing, again, setting the minimum density within the field of view of the sporadic E, and the FOE as setting the maximum density of the FOE within the field of view. So here, I've defined, so I have, okay, let's just zoom in. We have our normal E region trace. We have our sporadic E trace. Again, we have this downward structure and then a long flat bit. I'm defining this as our FOES and H prime ES. We have some F2, and we're getting multi-hops of this sporadic E as well. But even in regions where we're having multi-hop sporadic E, we do have clean F2 traces above that, or possibly F1. But you will see that we don't have anything in this region here up to this point. So what we do in our SEO Explorer is right-click, go down to the bottom of the list that comes up and click FBES and define it as this point here. So the minimum density of sporadic E within the field of view. This is another example, just to highlight that these things can be a bit more complex. This is one that I've scaled. So we have a couple things on here. One, we have a restricted band occurring right on our FOF2. So we have to use our X mode trace to try and infer some of that. I have a lovely overlay code that actually just takes my X mode trace and then projects it for me. So I don't have to make any guesswork about where this extrapolation needs to be. But more interestingly, and to the comment about, or the argument that Yvonne maybe and Tobias were having earlier, we can see this long flat structure at the bottom below our normal E region trace. And that's just sporadic E that's occurring at very low altitudes. It's likely a layer that is formed quite a while ago and is slowly being pulling down with the tide or the gravity wave that formed this sporadic layer is eventually going to go too low and it's going to dissipate. But it ends up below the actual normal E region peak. So then we have our normal E region peak, but then we have this thing. And we might have earlier classified this as sporadic E. But we have a cusp here on the F2 trace, which means that this bit here is either result of a tilt in the ionosphere or is the result of actually a thick secondary E region. This is just to give you an illustration of that. So this is a really great run of the Tromsø iSCAT inquiry and scatter radar. Ben's really familiar. I put this up a lot. Where we have a lot of things going on. One, you have particle precipitation. That's great. You've got a lot of TIDs modulating your F region here. But the most interesting thing or relevant thing for this conversation is that we have an E region that has actually been split into two, possibly even three, by the descending semidiurnal tide. And so what happens if you generate an ionogram out of that is you get your normal E region trace, and then you get a cusp, and then you get echoes from your second E region, and then you get a cusp, and then you get echoes from the bottom of your F1, and then you're into the F2 trace. These extra wiggles at the end are just because the resolution of this mode isn't good enough to be able to make these ionograms down here, but at these altitudes, the resolution is like 0.3 kilometers, so I trust that. But so you can see, you can get stratification of the E region, and there isn't an easy way necessarily within the tools that we have available to us to be able to separate out these types of layers. Often you will have to kind of make a judgment call about associating, say, this as one single E region trace and putting FOE here. It depends strongly on the circumstance. And again, what I kind of threw as an offhand comment is you can also get similar structures like this from tilts in the ionosphere, which are also typically associated with tidal operation on the lower ionosphere. And so even when you don't necessarily have a distinct separation in the region trace, you might have a tilt that will generate a similar looking structure in ionogram. So I guess my overarching comment here is it's complicated, and sometimes we have to be a bit, we have to make judgment calls. In this case, conventionally, if you had no other information to operate on, most people would probably consider this a descending sporadic E or a primordial sporadic E layer that'll eventually descend fully and thin out if there are metallic ions present. No metallic ions present, that eventually just kind of joins the rest of the E region trace over time. Which brings us well into tilts and stuff. And Tobias, how am I doing on time? Because I can stop at some point down my thing.
Then you still have 20 minutes before coffee break.
Okay. Yeah, I put a bunch of a couple of examples at the end of this, so it can extend or I can cut. But I'll get through the core topics first. I realize there's a lot of content here, and people are probably starting to wane. Oh yeah. Actually, any questions about the material to that point? Again, it's a lot of material. I realize there's a lot to absorb all at once here. You know, every complex thing in the ionosphere. Ideally, we'd spend half a day just looking at each individual one of these and trying to tease them apart and getting a lot of experience in the different types. But yeah.
This spread, in ionogram spreads, most of the time the second hub was having more spread than the first hub. What is the reason for that?
The second hub has more spread than the first?
Yeah.
Well, I wouldn't say it's always most of the time. I would say
Range spread or frequency spread? Well, the range spread, because the frequency spread in the second hop is usually far less, as both Ivan and David explained, because things will walk away if they are not vertical. But if you have range spread, Of course, if the range spread that is vertical, that gets added up with the second reflection and added again with the third reflection. So in the range spread, you do often see that indeed for this reason, because if you have a little bit of spread at the first hop, when the signals come down to the Earth, okay, they are all reflected at the same altitude, ground level, but then they go up again to the ionosphere, and then you will get again the same spreading, but from an already spread signal that was already spread by Earth. So that's
Exactly.
So in the range spread, you do see more spread in the multiple hops, and quite often even that the first hop might look perfectly smooth without any spread, and then in the second you do see. But that's for the range spread. The frequency spread, which is what we mostly was talking about, there it's the opposite. There usually in the second hop, you should not have. No.
Thanks.
Is that true for both the O and the X mode?
Yes.
Yeah, there's no reason why it should be different.
These things are the same for both modes.
Unless for like just by chance the X mode happens, because the O and X modes go opposite directions with respect to the poles. So we say they're vertical, but they've kind of separated quite a bit. So it's possible that the X mode's just gone into a place that has slightly more irregularities. So it can happen, but
And both could magnetic field effects exacerbate how that gets right?
Inhomogeneity in the magnetic field is usually even large swings in magnetic field would have to be incredibly large to cause enough perturbation in the magnet or in the gyro frequency to cause significant effects, at least on HF. On other frequencies, maybe not so much.
Was it also a case where we observed the Z mode?
Z mode. I'm not putting Z mode up. Z mode's fun, but it's a high latitude feature and beyond the scope of this. It's already too much material to talk about in one session, so it's too much. But Z mode is just you'll get another mode at half the gyro frequency on the other side of the O mode, so below the O mode. That'll come because of a coupling between the O and X modes when you propagate exactly along the magnetic field line, or very close to along the magnetic field line. And again, it can only happen really at high latitudes where you get that field line propagation. Anything else? Okay. Couldn't quite get to the break. No. Right, so traveling ionospheric disturbances or tilts, these often cause what we call stratification in the ionograms. We usually put on a descriptive letter H for these. Ionogram inversion as a concept, at least in the conventional way that we apply it, assumes that the echoes are coming from vertical. And anything that's not coming from vertical can't really be included in the inversion process. And so we need to be able to we need to be able to distinguish between what's coming from overhead and off vertical, and that's why we say with the spread F, we're looking for the things that were most likely to be overhead because we're trying to avoid violating this fundamental assumption. But this assumption is directly violated when the ionosphere is not horizontally homogeneous or flat. If it has strong gradients or irregularities, we end up with other structures in the ionograms that are not fundamentally adhering to this vertical propagation. A lot of these structures can often resemble F1 traces. This is a particular problem. It's one of the reasons why autoscaling tends to have a very, very hard time with the FOF1 because you need other information to be able to discern or separate this out from FOF1 or these wiggles that you get in the ionograms. Typically with TIDs, we employ similar strategies to what we do with spread F, but the easiest way to identify them and to try and deal with them is to look at a time history of ionograms. This is particularly important when we're starting to deal with trying to distinguish FOF1 from a TID bump. Angle of arrival information has made this a lot easier over time. We can definitely reject a lot more echoes than we used to be able to. But we'll just start off with an example case here. So this is a pretty standard Julius-Roux ionogram. We've got, FOE here, FOES here. It's non-blanketing. We have an F1 trace with FO, F1 somewhere around here. Then we have an F2 trace with an FO, F2 probably here. I would agree with Artiste on that one. Okay, so let's progress in time. This next time step, you'll notice that our F1 peak is just kind of flattened out or disappeared. You can see that the gradient associated with it is still there, but it's being counteracted by some sort of either restructuring the ionosphere or, as you might guess, given the topic, a traveling ionospheric disturbance, a tilt. We're getting echoes now, not from directly, or that are bending as they're going up and hitting the side of a structure instead of hitting the bottom of that structure. And so the virtual heights from that are going to be slightly different than what they should be coming from vertical. And so, well, now, you look at this, you might say, well, what? FOF1, isn't it here? Well, we talked before, but we know that FOF1 is pretty stable. So FOF1 increasing by a megahertz and a half over one time step is a pretty generous ionospheric disturbance. That you know, if we had a huge flare or something in the middle, but then we wouldn't have an ionogram. So this bump should be suspicious. And if you're aware of where your FOF1 roughly should be, this should kind of stand out to you. And if you progress the ionograms, you can watch as that bump just moves its way down the ionogram and eventually off. And then you can see our FOF1 pop out the other side once the layer is flattened out again after the TID has gone through. Interestingly, often when these TIDs move through, they're gravity waves, so they'll compress the E region as well. And so you'll often also start to see tilting in the E region trace, or you might start to see sporadic E or these kind of secondary E region traces as well, making their way through. And so here, again, FOF1 is now here around 5.6 or so megahertz. It's sunrise, so the value has increased from what we saw before.
Are you sure?
Hmm?
Because the predicted value is at 3.9.
Note the date of this ionogram. So this is actually a good example of not necessarily always trusting these, and instead just trusting an ionogram that you know is smooth. I know this is a very flat, clean ionogram. I know where FOF1 is from this. I don't need to look at the predicted values to get that. But I can look and say, oh, well, my predicted value, it's at 3.8, but my true value is at 5. Why is that? This is from last week. This is from 2 days ago. We have incredibly high solar rotation changes in solar flux right now. And so on the order of 100%. So the model that's being used to generate these predictive values, one, because it's so close to current time, might just be a bit old. It's using forecasted instead of real values. So it doesn't have the big jump in solar activity that we've recently had. And so it's under-predicting the modeled FOE and FOF1 values. Anytime that you're dealing with data very close to current date, just generally you might want to have a bit more of a reservation about the predicted values. And again, as Yvonne said, update your local database of the sunspot numbers that you use for deriving these values. Of course, they're quite smooth, and they might not capture, even if we look at this months from now, we may end up with the same result, because this is a solar rotation timescale variation, and they use R12 to drive these models. Anyway, point is, yeah, thanks for bringing that. That was one of my key points that I forgot to mention. It's also kind of highlights a little problem here as well, where the ionosonde or the ionoscaler is a bit too pinned to climatology. It's saying FOE is here, close to the predicted value. It's very clearly a little bit higher than that, right? That's not always the case. If you go later on, you can see, let's see. So we've reestablished our F1 layer. This is a clean ionogram, very well scaled except for the E region trace here.
Can I make a comment here? Because
Yeah.
I want to point out something specifically about this, what you just mentioned about the E region.
Yeah.
Because this is the paradox that if you use ionosome data in your own research, you will often run into this problem. You use data that has been derived by the software. Many people do, rather than looking whether it's correct. But the software itself is using these predicted values, especially for the E region, to help itself in interpreting the data. So you have a climatological model. The software uses that model to help it interpret the data. And then you use those interpretations in your research. But what you're then looking at actually is just this climatological model that was fitting at the very beginning.
Now, like,
And then
it can be.
comparison between the observations and the climatological model and come to the conclusion that there is little difference. Right?
Yeah, this does highlight the need for manually scaling ionograms, particularly with these, again, these highly, well, generally we accepted predictable values. But like, I used to see Chilton in 2013, solar activity increased by a factor of 100 in the month, and FOF2 ended up getting kind of cut off at some fixed distance from the predicted value because it was just way too high compared to what it should have been. And so it's unreasonable. The autoscaler thinks it's doing something wrong. It'll try to recover from that. Again, Yvonne can speculate, I guess, as to how that's actually happening. But regardless, this is a bit of an extreme case. Again, it's a very recent period. It's high. It's again, we're having these very large swings in solar activity. This is an anomaly rather than the norm for the autoscaler. So again, life is good. Let's just go here. I was just going to point out that by the end of this period, Artis has correctly picked out oh no, it hasn't. No, it's correctly picked out the FOF1 over time as well. So it took a little bit. Generally, Artis will opt to not put FOF1 on it. It's Yvonne, correct me, but it tends to be more conservative when assigning FOF1. I assume because there's so many things that can cause things to look like FOF1, but it's better not to assign something if you're not certain about it. So. TIDs can also cause forking in the traces. So this is just a case, more sporadic E. We have lots of blanketing now, up to about here. And then FOES is around here. Our normal E region is here. And then we have our F region trace where, based on the time of day, I suspect we are missing an F1 trace that should be here. This ionogram generally would be best probably not to scale. There's enough of the trace missing, of the structure missing, of the substructure missing, that I would not try to create an inverted profile from this. However, what you can do is identify the parameters that you can clearly identify. Again, all of our sporadic E parameters and E region parameters, where is this gone? Thank you. Are clear. Our FOF2 is really clean. So these are things that we can recover from this ionogram. We can progress in time a little bit. Same type of thing with this one, really clean F trace. Again, I suspect based off the blanketing that's severe enough that we're missing an F1 trace. And because we have no inklings of the F1 trace, I would generally recommend not scaling the trace of this ionogram, and instead just putting in a value for FOF2 and keeping your E region parameters. Still moving on, much the same. And then you see something interesting. This little guy here. This almost looks like when I showed you G condition before, where the F trace descended and evolved downwards and forward. But this is actually a TID. This is you're getting echoes from vertical, and you're getting echoes from the crest or the side of a TID structure. They're both coming back, and you're getting slightly different virtual heights from both. Despite what the angle of arrival information is telling us here, I have high confidence in scaling this as the vertical trace. We see corresponding information from the X mode and from the echoes above. And you can see above these, V is starting to come off oblique from the second hop. You move forward in time, and unfortunately this ionosome is really coarse. It only gets an ionogram every 15 minutes. So this TID structure, we expect what's going to happen is going to move its way down the trace. Same as that bump did before. In this case, that fork is going to move down, and that junction point is going to move down with it. As you go from having the trough of the TID above your head to then having the crest above your head and the trough on the side. And so eventually, you're going to have to migrate from scaling echoes that are coming from the trough, the TID, to ones that are coming off of the crest. And in this case, again, this is not me scaling. It's a really complex ionogram. Like this is hard. We've got, again, normal E region, sporadic E, FOES, and H prime ES over here. We've got blanketing up to here. And then we've got 2, 3 even F region traces. In this case, we've got, well, if we had higher time resolution, we could see this was effectively where our original trace is, and this is where the crest of the TID is coming through. We've got good alignment of this lower echo with a coherent set of echoes from the upper trace. And we again have a nice X mode associated with this, whereas a less well-defined, a more complex X mode from the TID trace. So in general, in this case, Artis is actually correct. This would be the dominant trace, and this would be the trace out scale. This is the most overhead trace in this circumstance. Doesn't really matter though, because again, we're maybe just about to see the F1 peak pop out of here, but we're missing so much of this that I might not try to invert a profile of this. I might still just try to identify F2. Which example is this? I've forgotten my own examples. Oh, that's really not a great one. In this case, as you were pointing out before, you can get quite a bit of height spread in the second hop, and you're seeing that right here. We have a little bit of spread in our F region first hop, and that has just been accentuated into almost 2 separate echoes into the second hop. We progress to the next ionogram, and I did this poorly because I cut off my second trace. But we have clearly defined E, F1, and then F2 into this dominant trace here. Again, the X mode here is doing a little bit of work in getting a bit more confidence into which echo to scale. Again, they're going slightly different directions with respect to north. So if there is a TID of some scale, how do I put it? If you're getting echoes that are coming off of the tilt and the and they're not north-south aligned, the O and X mode traces that are correctly coming off of vertical should produce roughly the same structure. If they're not, it generally means that one has hit the side of the TID and the other one has just kind of hit the normal vertical structure of the ionosphere. And so the X mode can do a lot to help you be able to scale some of these TID cases. Not always, but it can be helpful. And I think we're at break now, aren't we?
Yes, but